Start. Are we sharing? Are we fine, Mariusz? Are we fine?
Yes, we are fine. We are on Zoom and we are on YouTube.
Oh, we go. Okay, so good afternoon, everyone. Today we have a visitor from CAMK, from the Copernicus Astronomical Center. And Heitor is working on some spectroscopy abundances of stars and some other stuff that he will tell you about. Heitor was doing his PhD and also graduated his studies in Brazil. And then he moved to Sweden for a postdoc. He was in Lund, spending some time. And now, a few months ago, he joined the team of Rodolfo Simiani that is in CAMK. And he's going to share his results with us. So, yeah, thank you. And the floor is yours.
Thank you for the introduction, and thank you for having me here today. So my idea is to present, first of all, how can we interpret some stellar populations, and to walk you through how one can do that. But first, I will start with the scientific motivation, or the main scientific question of this work. It's basically, how can we understand our galaxy and trace back its formation and enrichment, and how we get the galaxy we see today. So as you may know, our galaxy is like a result of merger after merger and self-enrichment. And it's in the process of accreting the small galaxy in the region. So in the past universe, it was smaller than it was accreting its nearby galaxies. And then we call it basically the reactive galaxy formation. So here we have like a merger tree. As you can see, the merger tree, it's nice. So here we have the merger tree. So here's can you see my cursor? Oh, yeah. Great. So here is the time. So we have at the beginning of the universe, form stars, and then they get together and they start like forming small galaxies. They merge, some survive for longer and merge to the big galaxies, and so on. So, but it's important to highlight that these small galaxies, they also have their own history, their own star formation history. So they form stars at their own pace, and they enrich its environment before merging to a bigger galaxy. So the idea here is that we have the galaxy A that forms stars, have its peculiarities and enrichment at its own pace. So, reservoir of gas and so on, and we have the galaxy B that also has its own history. And then now we see today in the Milky Way, it's a result of all these mergers that is going on and result in a bigger galaxy that we can see. However, the idea is, can we trace back, can we see galaxy A within C? Or can we recover the original galaxy B that's now we see? So we have I think a zoom in simulation on a group from Oscar Argents in Lund called Vintergatan. That's basically Milky Way in Swedish. That's winter way. And they try to run the simulations and pick the galaxies that are similar to the Milky Way we see today, and then try to understand what happened in the past. And there they see that they have at least one bigger galaxy and one reasonably sized galaxy in this case, and they merge together. And then that's what we see today. And then they can trace back the gas, the assemble of the gas for the bigger one, if it is a merger, what they call, and where the stars of these previous galaxies is sitting in the Milky Way today. And then with several simulations of that and the angle they fall in, you can understand through simulations how we see these populations today within the galaxy. And now I will introduce you, if you probably don't know, or if you know, what is they call Gaia Sausage-Enceladus, and how can we find such populations in the Milky Way. So the idea, as I explained, is studying A and knowing C how can we recover that? How can we find even this population? Because it's hidden deep in our Milky Way today. So that's basically what we do is basically what they did here in Germany. So we try to find fossils. We try to find these hidden populations, which is not an easy task, but we try to find those and characterize those, which sometimes lead to mischaracterizations. When we think it's a dinosaur, maybe it's just like a dead chicken or something like that. So we need to really know what we're doing. But how we did for stars. So in 2018, Belokrov and Helmy, and in the same year, they did this analysis of the Gaia data. So that's Gaia data. And we can see here that when you got the V5 versus VR, we see a blob. That's the disk. But you also see a distinguishable body in this space. And this body just appears and vanishes. It depends on the window of the metallicity that we're analyzing. So it's quite prominent when you do like in this metallicity window of -1, -1.3. Between that, we see this elongated shape, what he called the Gaia, because it was in Gaia's data, the Gaia sausage. Helmy was doing similar things to the Gaia data. However, she decided to call it Gaia Enceladus, and now we call it Gaia Sausage-Enceladus. And just to give an example of the size of this body, because it was the largest major merger that the Milky Way experienced, it's about the size of the LMC in terms of mass when you analyze the mass metallicity relation. So it was not a small galaxy falling into the Milky Way. And that's how we find this mainly. We go to the kinematic space and we find these accreted populations in the Milky Way. However, you may see here, it's not easy to distinguish when it's close to the disk, or maybe if the population is within the pattern we expect for the disk for the kinematics is really hard to find. And then we go to more fancier space, so the action space, and we go to the angular momentum versus the action in square root of JR, and there is slightly more easy to find. However, you can easily see here that even this part here, it's complicated to find. And then people develop like different selection methods trying to find those populations. Because this one, the blue one is the Gaia sausage. These are other populations, and this is the whole disk. But that's basically an arbitrary selection that gives us the Gaia sausage. So you can see here, but in the Milky Way, just artistic expression of the Milky Way, and then the Gaia sausage, it's all over the Milky Way, especially in the halo, of course. And then for this study, we decide, for a simple study, we decide to use abundances to interpret this population. So we had a layer more than just kinematics. And interestingly, I studied in 2010, like 3 years before Gaia and 8 years before the Gaia sausage papers, they found a very interesting thing. So when they select high velocity stars around the solar neighborhood, because they're easy to observe, because they're bright, because they're nearby, they, in the alpha or MG abundance, they found two different abundance trends. One they simply called the high alpha halo, and the other one the low alpha halo. They had no idea what was going on, but they are clearly different. And it was a debate for some time about what are these low alpha and high alpha population. And now we see that it is likely accreted stars. And if you expand that, we move forward, we find that this is basically the same stars. And when we do the high alpha and the low alpha, here's the MG as before, so the same plot, just in different scale. When you analyze the alumna of those stars, especially in these UV lines here, we see that it's a clear separation. So they are completely different chemically. So we can use now chemical abundances to characterize this star, there was this like hidden by the kinematic area. So some are easy to identify, they are far away in the kinematic space, so it's easy. But when it gets more close to the disk, it's hard to distinguish. Now, how can we use these abundances to tell a story, to see what's going on with this population, what they experience? So the same way we did, we first identify those, now we need to interpret those. So the same way they do for dinosaurs, you need basically a toolbox to resolve that. So we need a knowledge on dwarf galaxies and their star formation history. We need some knowledge in nucleosynthesis to interpret what I see in the abundance space. We need, of course, kinematic data to resolve its population in the first place. And we need a good data set. We need also some completeness of this object that we want to analyze. So my idea was in this previous work was to compare with living, or the ones that survived, the dwarf galaxies that survived. For example, Phonax, the same way they do a comparison for like a living dinosaur, a chicken, we can do this comparison from this one is hidden in the Milky Way, it's dead now. We can compare to the living dwarf galaxies like Phonax. But also important for this to have different chickens. How can we extract? Because we have no knowledge about the star formation history in the Gaia sausage. So we need to compare with chickens that have different histories. So that we pick Phonax and Sculptor. Not just different history, we need a decent amount of data to be able to compare. So we need abundances, and we need stars, basically. With not trivial, some dwarf galaxies, these spheroidal ones, some have like very few stars analyzed in some abundance spaces. So just to give context, so Phonax, these dwarf galaxies in the solar neighborhood, have completely different star formation history as a Sculptor. So you can see here, so that's the beginning, so that's now. And we have the Phonax, it have a gentle star formation rate. So in the beginning, it starts to slowly forming stars until it peak, have some sort of plateau, and then it die out, like exhausted gas. It's from all the stars that had to form. While Sculptor have a burst start in star formation, and then use all its gas, form all the stars, not all, if you do a final analysis, but and then it basically sees the star formation. So it's basically quenched, and then it die out. So here we have a big difference, which is important for the next steps. Now, what do we need for in terms of stellar nucleosynthesis for now? So we have different elements, have different channels for its production. For example, the light ones, we have it from the Big Bang. The lithium beryllium is complicated. We have some light ones that we can produce inside stars. Like, for example, how we produce helium and carbon. We have like alpha elements together. We can produce those. We can well explain those formations inside stars. So we have like some energy budget to produce that. And we have the peak in iron, what we can do inside stars. And then here, the heavy elements, we basically need to go to this process here. That's the neutron-capture process. So here's just atomic physics. So we have a nuclei, and we have a lot of neutrons going against this nuclei. It captures some of those neutrons, and then it decays. So you can imagine that if you throw against this nucleus a lot of neutrons, it goes up in mass, but not in the atomic number, like in Z. And then it decays. And then it goes a lot, and then it decays, because here it reaches like a magical number. And then it goes. So then we can produce the heaviest elements we can find, like platinum, gold, the lanthanides, for example, as they are talking. And then we have the S process, the slow neutron capture process. And then you can imagine like it captures some neutrons and then decay, like beta decay, and captures some neutrons and the beta decay. And then we can produce some elements, for example, barium, that it's easy enough to analyze in this stellar spectra, and can produce the ones we find here in this area. So, and then we can produce, this is the R process path, this is the S process path, and then we have here what they will decay and go more to this center region that we observe, just for you to have a full perspective of this path, because here is just like a small subsection of it, how it works. However, you may ask yourself, okay, now I know how to produce those in terms of physics, but which stars and which phenomena can produce those? So different, like for example, the asymptotic branch stars, so these giants, they produce more S process elements because they're big, they have wings, and they can produce those. For the R process elements, the heaviest one we can find, we require more energy, and then we basically require some explosions. And then for this is still under some debate, which source, astrophysical source, can provide these elements to the interstellar medium. And then we can have the neutron star merger, and then we can have some core collapse supernova that can produce those R process elements, what some call the R core collapse supernova. Or any fancier model, for example, we have spinning stars, we have collapse stars, have all sort of things. But then with these elements, we can trace the evolution path of a galaxy that once born, the first stars had this production of the light elements. They explode, so we likely experience some core collapse supernova in the very beginning because this phenomenon is quite fast. And then maybe later some neutron star mergers in their system, and for sure some AGB stars. And here is about how we spotted this in the abundance space. So when you go to the abundance space here, in 90s they already figured out, the Matteucci explained the need when you analyze the alpha element. Because the alpha element is mainly added to the median by a core collapse supernova, so a massive star to explode. And then when you plot against iron, that's commonly added by a supernova type 1a, that's a delayed process, we had these knees, that meaning is that it has a basically fast star formation history when you go in this direction. Like the bulge or elliptical galaxies, and then the solar vicinity and the Magellanic clouds. Because basically is the time we produce a lot of oxygen in core collapse, and here is a plateau, and then the iron starts to appear in the middle. So then we have these knees. And now moving for the dwarf galaxies, that's what we have for the dwarf galaxies. As I showed before, but less detailed now, is the star formation history of Fornax, the star formation history for Sculpture, but the other way around. So flipping the previous plot. And for Sagittarius and the Milky Way. So this previous paper by Sculadorti and Salvatori, in 2020, they have this interesting idea of knowing the star formation history. What do we see in the abundance space? What do we see when it smartly plots some elements against other? And what are the differences? So here, for example, like it's the same plot as before, but the other way around. So it's iron against Mg over iron. So here we have the knees as before. So we have the Milky Way and the dwarf galaxies. When you look for barium, you can see that they have a completely different behavior. Some dwarf galaxies just go up, some starts more in a higher place and then continue and suddenly go up. When the Milky Way, it's about flat, is slowly going up in barium. When you go to European over Mg, interestingly, we have just flat for the Milky Way, which means that whatever source that produces European and Mg or is the same source, or they have at least the same pace. So they are equally fast in adding these elements into the medium. And when you compare fast, which should be fast, European against baryon, we have that for the Milky Way. So as late as it's going in star formation, the European for AGB starts as very delayed source. It starts to kick in and bring all these populations down. Unless you are like Phonax that don't have time to have the impact of the AGB stars showing the population they have today. So they just don't appear. It's die quite fast. There is no gentle moving here. But this up is quite interesting. I'll come back to this later. That happens for just these two dwarf galaxies. So here, just to put in picture the timeline of those events. So MEG basically simplified. It was produced by Core Cloud supernova with a fast source, with like about 0.1 giga-year. And then we have the core collapse, the supernova type 1a, that basically adds iron in more later times, because core collapse supernova can also put some iron in the environment. And then we have AGB stars that can have a huge range, but most of them are delayed. And in this paper, to explain this rise for the core collapse, for the European over MG, they said that for these environments, something is going on that is adding at a later times more European than MG. So they proposed, they didn't discuss which phenomena that can explain that, but they proposed that they need a quick source to have this plateau, so have the same pace as the MG for European. And they also require a delayed source that will kick in later in the star formation history of these dwarf galaxies. But now, knowing all that, how can we see that in the star formation history? How we can produce some qualitative star formation history, trying to identify the different patterns we see in abundances and how it connects in Phonax and Sculptor, just highlighting those now because they're the one that we use in our work. So there's two different shapes, just for context. So here we see that Phonax, at the very beginning, had very slow star formation history. So we can see here that in this part, it's basically flat. So whatever is adding European is adding MG in the same pace. That's okay. While in Sculptor, we see basically the same behavior. So okay, doesn't matter the star formation rate in the very beginning, we have European MG. So the except for a fast source to add European works in the very beginning. It's not star formation rate dependent. So maybe it's the first source. However, when it goes longer, we start to see a rise in Europe. So something is adding European. So it's a delayed source adding European that we cannot observe in Sculptor at all. So the explanation, well, possible explanation is Sculptor died before we could see the result of this delayed source of European, because we not only need this phenomenon to happen, for example, let's pick like star formation merger, neutron star merger. We need it to explode, pollute the interstellar medium with the elements, and stars to form from this material for us to see a star with higher European over MG. So likely, we didn't have enough time for this behavior to be shown in Sculptor. So then in 2020, Explorador and Observatory, they put a marker here. So we need a source that adds European after 4 giga-years, because that's when the Sculptor dies, basically. It stops forming star, they quenched it. And if you use more recent analysis, more recent star formation history for Sculptor, from Bettinelli, there's more, we can trace back for 2 giga-years. Now, keeping it in mind, we go back now to the Gaia sausage and how we can interpret that. So what they did in this paper, also Escudor did in her paper with Stefania Salvadori, they basically went this known star formation history and interpret the abundances. But now we only have the abundances. So now we can try to infer the star formation history for the GSE. We do the other way around. That for that, we want a lot of stars, the maximum we can get, with europium abundance, with barium abundance, with magnesium abundance, and iron. And then we went for this, for the literature, and no homogeneous data has the amount of stars that we want. So we want a larger sample that we can also test some selections for the GSE. And then we went for the SAGA database. I'm not sure if you are familiar with the SAGA database, but it's basically, it collects all stars that are in CDS and put it all together and all information about the stars. So a single star may have like 20, 30 references, and some references are just for TF, some references are for TF log G, and some references are for the abundances. So if these and the Gaia data, we combine those, and we get like 600 stars with europium and iron measurements, because that's the most principal one. So that was our first selection criteria. And we select stars with the range we're expecting the GSE, so minus 2.2 to minus 0.5. And that's what we have. So we're selecting those. That's a specific selection of the GSE, because we have many. We have like 5 or something that are more popular. In the paper, we discussed them all and the difference and why we pick one in the end. And then it was quite painful to do the data handling of this. Because, for example, we had a lot of stars in our sample that had just a single europium measurement, which is easy, we just got this one. And some stars that are quite popular in academia, people really like some very specific ones, and we had 11 measurements of europium. So we decided just a simple approach to just take the median of the TF, log G, and the abundances. Because the whole sample is a combination of more than 80 different works. And we had some uncertainty to put some weight in what we are doing. And then we had to select those. So we didn't start the selection because we didn't want any bias at that point. But then we had to test the selections. And here is the why it closed. And here we have the space. And here, for example, we have the original selection that Helm used. So we just cut in the angular momentum and some energy, like the potential energy in the Milky Way. So it depends on the potential that we were adopting on the Milky Way. And then we had Nido, that's a simple eccentricity cut, just quite clean. And we had the Diane Fourier selection that's in actions. And to decide that, we use another work that did some simulations with Auriga simulations and applied those selections. So they know this, they have a flag of this different population, like the Milky Way they have there, and the accreted body. And then they apply the selection check for completeness and the purity. For example, they found out that a selection that is just in eccentricity is the most complete one, as you can assume. It's just pick a lot of those stars that we have here. While the most poor one is the one that you'll be using the actions. So we have the angular momentum and the square root of JR. So we decided to adopt that because we're aiming for purity also, because we don't want the trends that we see in the abundances to be misled by some in situ population or the disk there. Because that can flatten out the trend. And then we applied these are the stars that should belong to the GSE according to the previous selection, and then we plot those here. So this is the data that's in the background that gives this the trends in abundance, that we use the same procedure as Isco did in their paper. So we can compare the overall trend. And you can see here that it's fairly good populated from the metal poor part to the metal rich, while the metal rich part not a lot of stars in the metal rich part, because they're really hard to find to belong to the GSE. So we have this metal rich tail, and also according to another study, another paper of ours, that the metal rich end should be deeper in the potential and then is easily mistook as the T stars. So it's hard to, we can flag those as the GSE, but we are not sure when we just do using kinematics. So it's not, this is why it's not well populated here. But now we put it always in this context as the same trend as before for Sculptor, Phonax, and the GSE. So the GSE is this magenta-like trend, and the Phonax and Sculptor are the orange and the blue, as before. So just to give overview, I go with individual plots here. There's all these panels A, B, C, D to explain what it means. But you can easily see now that there are more prominent changes in some panels than in others. For example, this one doesn't tell us a lot when you plot iron over Mg, besides some difference in the need. And then which information can you extract from each of those panels. So starting from this one, that's more easy to interpret. We have this part here that's the beginning of the altered galaxies. They're basically the same as you can see here. So we have just the balance here for the core collapse supernova, what it adds from iron, what's added from Mg, adding more Mg than iron. And then we start to have this distinction from when the supernova type 1a starts to add more iron in this environment. However, this difference is so little that we cannot overinterpret this is too much, and they start to open the other plot for that. Why do we have a hint here that it has a slow star formation in the beginning, based on this angle here, and that based on its mass and history, it definitely quenched earlier than it should, because it was accreted by the Milky Way, so it was murdered basically. So we see for sure that it was quenched. It didn't use all its gas to form all the stars that it should. When you go to the bottom of Mg, that we have, like, remember, a fast element, so it's a fast source that adds this element, and we have the more slow one in baryon, we have a big difference here. So the sculptor, that's quite interesting, this one, since it has a bursty star formation history, we have all core collapse supernova in the very beginning, basically, and then we have some Mg and no baryon, and then it just rises out adding basically baryon. So it's just a flat line that starts very low and go up. While in Phonax and GSE, they have a similar behavior in the beginning, suggests that the GSE has a similar star formation history in the beginning. So quite gentle and quite slow, and it slowly comes up. So we have a hint of the star formation that has a slow initial star formation rate. And when you go to the European of Mg, we have this rise here. Although it's quite interesting that we have a rise, and then we have like this debate from we need a fast source, but we also need a delayed one. However, in terms of star formation history, we can only add a marker here. So we know that it goes beyond, on the previous work, 4 gigayears or 2 gigayears. So it for sure crossed this mark. we have now a complete view when we put the European over Barium together. So similar for Phonex, it's quite simple. We have a high European because it's fast. We have this fast source polluting the media with a lot of European, and then it just goes down because we add barium. Meanwhile, we have a Phonex and GSE are basically flat trend. However, interestingly for the GSE, we don't see this downtrend, so we don't see the domination of the AGB stars in the later times because it probably was quenched. So we know here from this that it starts slow, now putting it all together, is extended here, is extended, and was quenched, all in a single plot. And quickly here, when we just compare to the literature, with whether we did make any sense, in terms of when you do properly the galactic chemical evolution models, Hasselquist in 2021 found a similar one. However, it predicts a burst in the middle for this behavior. So it's slow star formation, and then some more prominent one in the middle, and then it was quenched or killed. Yeah. And just as a summary picture, for putting it all together, what it should be in comparison with this marker. And now very briefly, some future perspective. Well, how can we improve this work? Because that was just basically an experiment on how can we do that, and if we can do that. So we basically, as usual, we need more observation, we need more data, which foremost for us will be quite handy, especially what they call foremost the S2 survey. That's dedicated for HALO, observe in the high resolution mode. That has some people that are interested already in pursuing this work, provide more data to fill this whole trend and maybe even correct the trend with better abundances, the more precise ones. And we do need tailor-made galactic evolution models to compare what we have, to have a complete galactic evolution models with like yields and everything. That's all. If you have any questions, I'll be happy to answer.
Thank you. So let's start. Any questions, comments? The presentation? So I have a question about if you measure abundances, I know that you were showing like in general the summary. How good spectra do you need for that? I mean, like, is one good spectra with signal to noise of, I don't know, like 50 enough? Or obviously it's better, or you need more spectra and you just average it? How do you deal with that?
So that depends for which element we're talking about. For this full work, the most complicated one is europium. Okay. That has a quite weak line in 6645 angstroms.
Okay.
And then for that, we need high resolution at least, okay, and some decent signal noise. What it means, like above 70. But the desirable is above 100. But
yeah.
So, but it's more meaningful that we have like high resolution, okay, with 40,000, 50,000. It's enough.
So. The foremost that you were showing, it's going to give you like enough resolution. That's right. So
yes, the high resolution mode, yes.
Okay.
But also they have a whole pipeline, so I hope that's still under testing.
But it's going to work this year, right? Or at the
end? Yes. They already have what they call the SPV, so they're testing the scientific data before. And this year they start doing. I mean, we start doing some pre-analysis and to see if the pipeline can deliver what do we expect, and if the data is good quality enough, deliver that.
Okay, please.
Could you please go back to the slide where it shows this discovery of the Gaia Enceladus? Yeah. So
Be this one?
yes. So X and Y are velocities. And the color scale goes from -13 to +13. But what are the units of the grayscale? Or like what's actually being shown that it can be negative?
That's a good question because I think in this work they use, I don't remember, but this group at least use quite often some column normalized or row normalized to highlight these differences in the different axes. I don't remember exactly what they did with this scale, but I think this structure for this is their first plot. But nowadays it's people do it and it's quite prominent. You can easily observe that. But I don't remember what the scale exactly is. But that paper is from Belokrov.
Excuse me, actually, what means -12 and 0.8 and 13.1?
That's from this gradient called this scale that I have no idea what it means. It's from the work. I'm guessing that's some column normalized, and I have no idea if it is the amount of stars or the difference from in each of these pixels. I don't remember from the plot.
Why we look at this?
Yes, from Belokrov in 2018. It's the first one that showed this body.
Any more questions, concerns? Have anyone on Zoom? I think we can just switch to that. So I don't see. I think. Yeah.
I also don't see any.
If there's anyone on Zoom who would like to ask, please do so. Yeah. And everyone is happy. All is clear. Very nice pictures. Very nice plots. Okay, so let's thank the speaker again. Thank you, Heitor. And next week we're gonna hear about some gravitational waves, right? From Neha. So yeah, looking forward. See you next week. The notebook is somewhere there.